6. This is Unit 5A, Probability. For our multiple choice test, this is Chapters 12 and 3 Review, multiple choice. All right. So here's the multiple choice. I gave you Chapter 11 also, but really number 1 is the only thing that will help you on this. Which of the following situations probably not truly random? Rolling a die is random if you shake it up and roll it like normal and don't try to make it a trick. Drawing a card from a well-shuffled deck should be random because there's no bias in there. This is the only one that should not be random, is because if you ask a friend to pick a number between 1 and 10, they may have a bias about one particular number. They may want to pick a number in the middle because they don't want to go low or high. They may want to go, all kinds of different things. So that would be the one that's not truly random. Okay, we're going to jump down to now Chapter 12, and I'm going to help you with the next couple problems. So Chapter 12, a fair coin has heads 10 times in a row. The probability that it will come up next is going to be, that heads is going to flip up next, is going to be 50%, because it's heads or tails, 50-50. And each flip doesn't affect the next, because you think about it, if I have a coin and I'm going to flip it, I get 50% heads and 50% tails. Well, it doesn't matter how many times I flip it. Each time I flip it, I have a 50-50 chance of getting heads or tails. So that answer is going to be B. Which two events are most likely to be independent? Independent means one thing doesn't affect another. Registering to vote and being left-handed, those don't seem to affect another. Having a car accident, having a junior license, well, yes, those are affecting each other. That's why insurance rates for junior license or younger people are more expensive. Doing stats homework and getting an A on the test, obviously as one happens, the other tends to happen. Having 3 inches of snow in the morning, being on time for school. Obviously, the more snow you're going to have, the later you're going to be. So those would be related. So yes, A. A friend of yours plans to toss a fair coin 200 times. You watch the first 40 tosses, noticing that she got 16 heads. Okay, so 16 out of 40 is 40%. So it wants to know, now I want a total of 200 tosses. So if I did 200 tosses and I got 40%, it would be 80 if I continued there. But this is shorter term probability. So it's not going to be 80, because 80 out of 200 is going to be too low when I start actually flipping the coin more and more. It's going to get really close to 50%. So 96 would allow me to have, when I tossed it the other 160 times, is going to get me something pretty close to about 50%. So 80 out of 160, tossing it, getting 80 heads out of total tosses. So 80 plus 16 is 96. 100 is an exact 50-50 split, which it's not going to be. And 116 is over a 50-50 split. So we know it's not that. Which two events are most likely to be independent? Again, two things that are not related to each other. Having a flat tire and being late for school. Well, yeah, if I have a flat tire, that is going to increase my probability of being late for school. Getting an A in math and getting an A in physics. Possibly that those could be related, because if you're getting an A in math and physics are related to each other. So, and maybe you have good study habits in both. So that may be related, but it possibly couldn't. So I'd put a question mark and come back to it. Let's see if we have a better one though. Having a driver's license and having blue eyes. Okay, those two, your eye color doesn't seem to affect you having a driver's license. Having a car accident and having 3 inches of snow today, those don't seem to be related to each other as well. So I would say, or excuse me, I said that wrong. Yes, having a car accident and having 3 inches of snow, the snow may increase your probability of having a car accident. Okay, number 5, a serial number is implanted on a medical device consists of 3 letters, 1, 2, 3, followed by 4 digits, 1, 2, 3, 4. The first number can't be 0. So how many serial numbers are possible? So it has 3 letters first. These 3 are letters. And so there's 26 letters in the alphabet. It didn't say I can't repeat them, so I'm going to put 26 times 26 times 26 times. The first number here, it said can't be 0, so only 9 digits to choose from, but all the others are 10 digits to choose from, 0 through 9. And if you multiply this out, you'll get C. A sandwich shop offers lunchtime meal combo consisting of a sandwich, a side dish, and a drink. You can choose from turkey, ham, or veggie. You can potato chips or salad, and coffee, soda, or iced tea to drink. So you have 3 choices times 2 choices times 3 choices. And that is going to be 18. Number 7, it says, which is the following probabilities are equal? Well, you can put all these into your calculator by menu, probability, and then this would be a permutation, would be the P, a combination would be the C. So you can do that, and I'm going to show you that in a second, but let's talk about why these are. So let's look at the formulas. For the C, if I have NCR, that would be this. NCR is this, n factorial over n minus r factorial, and then r factorial. So if you notice, those two add together to be n. So for instance, if I had like 12 choose 3, that's going to be 12 factorial over 12 minus 3 factorial, and then it's going to be 3 factorial. So that's going to be 12 factorial over 9 factorial times 3 factorial. So then let's look at 12 choose 9. So what's going to happen there? 12 factorial over 12 minus 9 factorial, and then times 9 factorial. But you can see that's going to be 3 factorial, and that's going to be identical to what I just had. So this one and this one are identical to each other. But then let's look at the other ones and see. So this here, 12p3, that's equal to 12 factorial over 9 factorial. Well, then it's over another 3 factorial, and we're back to what we just got over here. So this one is also identical. This one here is 12 factorial over 9 factorial, and so it's not quite the same. You can also put it in your calculator, as I said, menu probability permutation, and then you would type in, so it would be NPR 12,3 for that first one, NCR 12,3 for the second one, NCR 12,9 for this one, and this would be NPR 12,3 over 3 factorial. By the way, the explanation point, if you look at the G on your keyboard, it's the button to the right of the G. Number 9, which of the following situations involves a permutation? Now remember, a permutation, order matters. So if I have 3 people and I have a first, second, and third place medal, obviously the order is going to matter for, let's say, Annie, Barry, and Charlie. It could be Annie, Barry, and Charlie. It could be Charlie, Barry, and Anna. Anyway, it could be all kinds of different permutations. So it says, a game show host selects 4 people from the audience to play a game. That doesn't have any particular order, so that's not it. Students are assigned seats in a study hall. Well, yes, if I'm assigned a seat, it's going to matter which order I can be in. So that one would be 5 law interns are chosen to help a lawyer. Those are just people that are chosen, so it doesn't matter what order they come in. A large group of friends at dinner will choose 3 desserts. So no, that one wouldn't be. So B definitely is the answer. Which of the following situations involves a combination? A combination's order does not matter. A lottery player selects 6 numbers to play out of 48. Well, this would be a permutation because I've got 6 different, I could put the number in all kinds of different orders. A bank customer chooses a new ATM code. Well, you can choose, if it's, let's say, a 4-digit code, you can choose the number's going to be anywhere. So that's a permutation. A survey asks to respond to rank political candidates in a certain order of preference. And that one is going to be political candidates in a certain order of preference is going to be, if I'm ranking them, if I have candidate A, candidate B, candidate C, or I could have B and A, then C. So the order is going to matter on that one as well. And D, every summer the school custodian changes the locker combinations. Well, you can change the locker combinations to anything that you want. And this one here, it's the answer key is saying A, but the way I'm reading it, I'm disagreeing with it. A lottery player selects 6 numbers to play out of 48. But if I select 6 numbers, I can put them, oh, yes, okay. Okay, I'm agreeing with it now. Sorry. Well, I'm glad I kind of got it wrong because the way I looked at it is that 6 numbers, like there's a 6 numbers on the lottery ticket and you choose the lotto ticket. But if you look at it more careful, it just says they select 6 numbers. It didn't talk about the order you're putting them in yet. You're just saying, okay, 10, 14, 50, 24, 30, and 6, where you're just giving the numbers, not a specific order to the numbers. It's just saying for one ticket. So yes, that would be combination. Okay. Chapter 13. According to the U.S. Census Bureau, 83.8% of U.S. households own the computer. What's the probability that 3 randomly selected households will have at least one? Well, at least one, if you look back at your notes, I have you doing 1 minus the probability of none. So the probability of none is going to be 100% minus 83.8%. So that's going to be 16.2%. And so 16.2% would be 0.162 times 0.162 times 0.162. And this would represent 1, 2, 3 people that did not own a computer. And so 1 minus 3 people did not own a computer is going to be the opposite of at least one person. One person could have the computer, or 2 people, or 3 people. And that answer is going to be 99.6%. Number 2, according to the U.S. Census Bureau, 74.4% of the households had internet access. What's the probability that 4 randomly chosen households all had internet access? So that's going to be 1, 2, 3, 4, and you're going to put 74.4% times 74.4% times 74.4% times 74.4%. And that is going to be 30.6%. Your friend tells you that when you're drawing a card from a standard deck, a probability of a jack or a king is equal to probability of jack plus a probability of king. Let's see. It's asking if your friend's correct or incorrect. So yes, I agree that they're correct because I'm asking for, here's the deck of cards, right? And I'm asking you to pull one from there, just one, and I want it to be a jack or a king. So I would add up the probabilities to get a jack, and then I would add up the probabilities to be a king, because the probabilities of a jack or a king, if I'm selecting one card, are disjoint events, disjoint or mutually exclusive. Because they're disjoint, we would add them because there's no overlap. Number 4, your friend tells you that when rolling 2 dice, the probability of 2 sixes is the probability of 6 times the probability of 6. And these represent independent events because one event does not influence the other. And we know that the probability of A and B, if A and B are independent, is the probability of A times the probability of B. And so yes, we agree that A, they're independent. Your friend tells you that when drawing a card from a standard deck, jack or heart is equal to jack plus heart. Well, the problem is that I can have jack of hearts. And so when I add jack together, I get a 13 out of 52 probability, because let me just backtrack real quick and let you know there's hearts, diamonds, there's clubs, and there's spades. And really I should have done it in the color they are, because the spades are black, the clubs are black, the hearts are red and red. And there's 13 of each. 13, 13, 13, 13 for a total of 52. All right. And then, so you can see that I will have a jack of hearts, which means I have 13 out of 52 jacks, or excuse me. There's one card in each one. So since it's 4 suits, 4 out of 52 jacks, right, is a probability of getting a jack, plus 13 out of 52 hearts. However, I have a jack of hearts, so I need to subtract 1 out of 52 because the jack of hearts got counted here and the jack of hearts got counted here. So that's why the answer would be no, and that would be D. They're not disjoint, and so you can't just add. You add only disjoint events because I have an overlap, and so that would why it would be no. Your friend tells you that when drawing 2 cards from a standard deck without replacement means taking it out and not putting it back, The probability of 2 queens is probability of queen times the probability of queen. Okay, the problem is I'm wanting 2 queens. So the probability of a queen is going to be 4 out of 52. And the probability of a second queen is going to be, if I'm without replacement, is the probability of the second queen, because I took one out. Now I have 3 queens left because I already took one out. It says I'm not replacing it. So here, let's say I took the queen of hearts out. Let's put a hearts, queen of hearts. So now all I have left is to choose from. I have the queen of spades. I have the queen of clubs. And I have the queen of diamonds. So I only have 3 of those left. And I only have 51 cards left, so therefore they do influence each other, because you can see since I took a queen, I now only have 3 left, and so you can see that that's the problem, and therefore it is not independent events, because you can see depending on what card I took results in the probability of my another queen increasing or decreasing. Number 7, okay, for the probability model to be valid, you need all outcomes to add to 1. And then all probabilities need to be between 0 and 1, because 0 meaning 0% possibility and 1 meaning 100% possibility. So each probability. All right, so all outcomes add to 1. Let's check it. 0.2 plus 0.2 plus 0.2 plus 0.2 equals 0.8. So that's out. 0.25 plus 0.25 plus 0.25 plus 0.25, that equals 1. And each of these are between 0 and 1, so that would be okay. 0.7 plus 0.2 is 0.9, plus 0.1 is 1. So that's equal to 1. And each of them are in between 0 and 1, so that would be okay. This one's 100% of the chance, and these are 0. And so that's 1, and each of them are between 0 and 1, so that's okay. So the only one that's bad is this one here, is A. A probability model that is simply a list of outcomes and the probability of each outcome, which is legitimate. So this is legitimate. 0.3 plus 0.25 plus 0.25 plus 0.25, that's 1.05. So that's over 100%. You can see each of these are valid here, but the total is not valid, so that's not valid. 0.01 plus 0.02 plus 0.03 plus 0.04, that's going to be 0.1, actually, not 1. Each of the one individually are valid, but just the total is not equal to 1, so that's not equal to 1, so that's why it's not valid. This one, 0.2 plus 0.3, is equal to 0.5 plus 0.6 is equal to is equal to 1.1 minus 1.1. So this is equal to 1, so that's okay. But however, that is not okay. You cannot have a negative probability. So that's not going to work. And then this is 0.2 plus 0.25 plus 0.35 plus 0.2. So we have 0.4, 0.6, 0.9, and then 1. There we go. And that is, everything looks good here. And this one looks good, so is legitimate. The answer key says B on here, I just noticed. But no, B is not right, because you can see that 0.01 plus 0.02 plus 0.03 plus 0.04 is going to equal 0.1 and not 1. So that's definitely not right. So this has to be correct. All right, I hope that helps you. Do well. And, oh, I guess there's 2 more. Oh, sorry about that. Oh, I guess the answer key doesn't say that. I was looking at the wrong one. The answer key does say D, so we're good. Sorry, I was looking at the wrong one. All right, we have 2 more. According to the U.S. Census Bureau, I have 42.8% of U.S. households connected to the internet using cable, while 33.1% uses mobile, and 21.2% is DSL, and 1% is dial-up. No internet connection was in 25.6% of the home. What's the probability the randomly selected household had either cable or mobile? All right, so we do know that cable is, let's see, where we go. cable was 42.8%, and mobile broadband was 21.2%, and we had dial-up was 1%, and none, we had 25.6%. Okay, so what is the probability the randomly selected household had either cable or mobile? Now, I know that cable is here and mobile is here. Now, if we add all these percentages up, let's add them up and see what we get. We get 8 to 1.6, and then carry to 1, we have 2, 3, 4, 5, and then we've got, yeah, we're close to 100%, right? So a little over 100%. So we've got some small overlap is what it looks like. Or, yeah. Let me double check here. And then, so the problem is I have cable is here. So you would say maybe 42.8, and then you could say plus 21.2. But do I have any that have cable and mobile? If I do, I've double counted, and I would have to, and I would not, it would not be able to be determined because I don't know if they have two. Now, I would be tempted to say, yes, I think they do. But the problem is when you add this up, sorry, not 100, it comes up to 90.6%. And so since this comes up to 90.6%, I've got a missing percentage. I don't really know everything, so it can't be determined. Okay, and then finally, the last one. And this is according to the Census Bureau, 42.8% of households are internet in 2013. If households called at random, what's the probability that the first house with a cable modem will be counted on the third call? So 1, 2, 3. So this is no. So 1 minus 0.428 times 1 minus 0.428 times 0.428. So we're going to multiply all of those, and when you multiply them, you actually get 14%. And 0.428. There you go. That's it. If there's any other questions, please let me know. Hope this helped.